Hello, this is Trevor from Telecom Training, and today we're going to be talking about the log periodic antenna, abbreviated as LPDA. The LPDA antenna looks very much like the Yagi antenna, but it works much differently. Now here we have both a Yagi antenna and an LPDA antenna at the bottom. Now the Yagi antenna has a dipole antenna in the middle, a reflector element at the back, and director elements at the front. Now the dipole antenna is the only active element that the Yagi antenna has. All of the other elements are passive elements. Now the LPDA antenna has all active elements. These are all dipole antennas, and they all operate at a different frequency. So this is what makes the LPDA antenna so attractive to many, because it could receive and transmit many different frequencies simultaneously. So this antenna can be used as a TV antenna, it could be used as a Wi-Fi antenna, and it can also be used as a cell phone antenna. So this antenna has many different applications. So I decided to build an LPDA antenna to increase my cell phone signal strength while at home. The reason I picked the LPDA antenna is because of its ability to transmit and receive a wide range of frequencies, unlike many other antennas which can only tune to one frequency. Here are some of the most common frequencies that you may receive from the cell tower. Now, I have the low frequencies here, which are in the 700 megahertz range. If you are far away from the cell tower, you will see these lower frequencies. Being a bit closer to the cell tower, you'll see the mid-band frequencies. And if you're extremely close, which is within a kilometer of the cell tower, you'll see these very high frequencies. Before building any antenna, you need to know the frequency you need to receive or transmit. So the first thing I did was to install an app on my cell phone called NetMonster, which is available on the Android App Store only. If you have an Apple phone, there are other apps on the Apple platform that will do the same thing. Examples are Network Cell Info, LTE Discovery, and Cellular Z. If you will take a close look at the phone, you'll notice that I have 850, 2600, and 1900. These are the frequencies my phone is using to receive and transmit back to the cell tower. I'm going to use these frequencies to design my antenna. Now these are the frequencies that I'll be using to receive and transmit from my cell phone. Under here you'll notice I have low frequency 800 megahertz and high frequency 2700 megahertz, but my frequencies receiving are only 850 and 2600. So what I did is to increase the range. You see, with the LPDA antenna, you need to have a range, the minimum range and the maximum range. Don't worry about what's in between, because once you have a range, you'll be covering everything from 800 megahertz to 2700. So I start a bit lower than I need, and I go up a bit higher than I need. So now I'll be starting at 800 megahertz, and I would go up to 2700 megahertz, and that would be my range. So the first thing I do is to find a wavelength of 800 megahertz. So how I find the wavelengths is to use the formula wavelengths equals speed of light over frequency. So the speed of light is equal to 300 million meters per second, which is 3 times 10 to the 8. So I took the 8 zeros off the 300 and plus the 6 additional zeros. That would be 8 zeros off, and I make it 3 times 10 to the 8. And underneath here I have 800 megahertz, so it's 806 zeros. So I have 800 times 10 to the 6. So when I divide 3 by 800, I get 0.00375 times 10 to the 2 by subtracting 10 to the 8 minus 10 to the 6, and I get 10 to the 2, and this is all meters, which is equal to 0.375 meters. So to get rid of this 10 to the 2, I just move my decimal point over 2 places, so I get 0.375 meters. So my wavelength would be equal to 37.5 centimeters. So centimeters, you would move the decimal point 2 places to the right, so I get 37.5 centimeters. This is a full wavelength, and dipole antennas use half a wavelength. So we'll be using 18.75 centimeters to make the first and longest dipole. Now as for the high frequency, it's the same idea. We just do the same speed of light over frequency again, 3 times 10 to the 8 over 2700 times 10 to the 6, and we got 0.1111 meters, which is equal to 11.1 centimeters. And half of this wavelength is 5.55 centimeters. Now under here we have our longest element, which is 18.75 centimeters, and we have our shortest element, which is 5.55 centimeters. So the next thing we have to do is to calculate how many elements we need between the longest element and the shortest element. So what we do next is to calculate the total number of elements that we're going to need to build our antenna. So we use the maximum frequency, which is 2700 megahertz, divided by the minimum frequency, which is 800 megahertz. So we get 3.375. So what we do now is to divide the log of 3.375 by the log of 1 divided by 0.9. Now, you're probably thinking right now, well, where did he get 0.9? Well, I'll tell you where I got that from. 0.9 is the scaling. If you look over here, these are the antennas here. This is the antenna going from the longest one, which is 18.75 centimeters, down to the shortest one, which is 5.5 centimeters. How we get it there is by scaling, is by making each one a bit shorter. And we have to decide what that scaling is going to be. Now, we have a scaling factor between 0.85 and 0.98. For LPDA antennas, we use 0.9. So that's where we get it from. So we use 0.9 here because this is what is common for LPDA antennas. So we divide 1 by 0.9. Okay, and we get 1.111. So we bring the log of 3.375 over to this side, and on this side here we have a log of 1.111. Okay, it's that simple. All we do now is to get our scientific calculator out, and we type 3.375, and then we hit the log button, and we would get this number 0.5289. And we do the same thing at the bottom here. We type 1.111 and we press the log button, and we will get 0.0458. So we just do our simple division now. Divide 0.5289 by 0.0458, and we will get 11.55. So we round that off to 12. So we have 12 elements. So we have 12 elements from the longest one right down to the shortest one. Now here we're going to use the scaling factor that we talked about on the last slide to calculate the length of our 12 elements from the longest element, which is 18.75 centimeters. Now we have to calculate the length of each one of these elements from the longest one right down to the shortest one at 2700 megahertz. Now up here we have the 37.5 centimeters, which you know is the full wavelength, and we divide that by 2, which is 18.75 centimeters. And that is how we get our longest length here. Now we multiply that 18.75 centimeters by 0.9, which is the scaling factor we talked about earlier. So this 0.9 really is 90%, which is equal to 16.875 centimeters. So we have here L2. L stands for the length of the second element, which is 16.875 centimeters. So this is 90% the length of the one before it. So this is 10% longer than the second one. So in order to calculate the length of the third element, we would multiply 16.875 by 0.9 and we would get 15.188 centimeters. So this one would be 90% the length of that one, which is 10% shorter than the one before it. So we would do the same thing for the fourth one. We would multiply 15.188 by 0.9 and we would get 13.669 centimeters. So we will continue doing this for all of the elements until we get to the shortest element at 2700 megahertz. So this is how we calculate the length of each element from the longest element to the shortest one when building an LPDA antenna. So now we have to calculate the spacing between the elements from 800 megahertz down to 2700 megahertz. We calculate the spacing using a factor of 0.05 to 0.2. This is the spacing that we would use in here. Now if we use a spacing that is very narrow like 0.05, our bandwidth become quite high, which is a good thing. You have high bandwidth, but the signal become more omnidirectional. It starts to change from being directional to omnidirectional. And the reason you have this antenna is to have more of a directional signal. You want to point that signal in a specific direction, like in the direction of a cell tower, for instance, in order to get the maximum strength signal transmit to that cell tower and receive from it. As you move the elements further apart, you're going to find that it become more directional, but you're going to lose bandwidth. We find that by using 0.1, which is about the midpoint between 0.05 and 0.2, we find that this is the best point for the LPDA antenna. We get the best of both worlds, having it right at 0.1. So what we will do is multiply 18.75 by 0.1 and we will get 1.88 centimeters. So that's how we get the distance between these two elements. And we will do the same thing for the second element. We will just simply multiply 16.875 by 0.1 and we will get this distance here as well. So we'll just continue doing that for each of the elements until we get right down to the last one. For the last element, we will multiply 6.538 by 0.1 to get the distance here of 0.654 centimeters. Now this is what the dipole antenna would look like. The boom down the middle with all of the elements connected. And remember, each one of these elements are divided in half because these dipole antennas represents two elements. For example, our first wavelength was 18.75 centimeters. I divide that by 2 to get 9.378 centimeters for each one of them. And that continue for all the others. And also remember, if you're using a metallic material like aluminum for the boom, you should use some sort of non-conductive spacer between each element and the boom to prevent shorting. So here we have our transceiver connected to a balun, and the balun is connected to our antenna. Now pay close attention to the wiring as it goes out from the balun and how it is connected to the elements all the way through the antenna. Now this is done with both wires, not just one. Both wires are connected in this zigzag pattern. And now if you build this antenna in the way it was designed, it should be 50 ohms. Your coaxial cable is also 50 ohms and your receiver is 50 ohms. So you should have impedance matching. But the problem here is is that you don't, because the coaxial cables is an unbalanced medium, where your dipole antenna is a balanced medium. Because both of these elements are the same length, they're identical. However, the medium in the middle of the coaxial cable is just a solid copper wire. But outside of the coaxial cable, we have the braided shield. And there are two different types of mediums. So this is called an unbalanced medium, where the dipole antenna is a balanced medium. So we can't connect an unbalanced medium to a balanced medium. We'll get an impedance mismatch, even though they're both the same impedance to begin with. But by connecting them, you'll get an impedance mismatch. So that's why we have the balun transformer to match the coaxial cable to the antenna. So this balun transformer would be 50 ohms, of course. It will be unbalanced to balanced. So you'll get an unbalanced to balanced 50 ohm balun transformer. So at this point, this LPDA antenna should be capable of transmitting and receiving frequencies between 800 megahertz and 2700 megahertz. This is Trevor from Telecom Training. Thank you for watching. And if this video has been helpful to you and you would like to see more videos like this one, please don't forget to like and subscribe. See you in the next video.